Okay, off we go. So last time we were talking about this idea called flux. Okay, so we're getting started now. So please recall that we were talking about this idea called flux, and the reason we care about flux. Okay, the reason we care about flux is that it's the answer to a natural question, right? And that makes something interesting. If it's the answer to a natural question, then it's worth talking about. In fact, what we're going to see here, and we almost had time to talk about this last time, and the clock ran out. I just didn't quite have time to do it. Not only is flux the answer to this natural question, what is dV dt? What's the volume per unit time of fluid flowing through this thing? It's actually also the answer to a different related question. And let me talk about that a little bit. Oh, let's see. You know what I can do? I can hit that, but there we go. Okay, so flux, this expression, was the answer to what is the flow rate with the understanding that the vector field represents the velocity of the fluid. Right, so that was the sort of the setup, right? The premise was that the vector field represents velocity. The question was what is volume per unit time, and the answer was flux. So here's the next question. The next question is, the context is, what if the vector field doesn't represent velocity? What if it represents density times velocity? Seems a little weird. Why would I want to multiply density times velocity? Really not clear what an odd little combination one would think. But if you make your vector field be density times velocity, and then if you ask what is the mass per unit time of fluid, not volume per unit time, now mass per unit time, the answer, again, is flux. Right? So flux is now the answer to two natural and interesting questions. If you want to know volume per unit time, set up your vector field like this. Answer is flux. If you want to know mass per unit time, set up your vector field a little bit differently. And again, the answer is flux. So flux is a really interesting thing. Now, by the way, this is the tip of the iceberg. Flux is a powerful tool when you're studying E&M, right? Electricity and magnetism. It's a really big deal. It's one of the primary players in what's called Maxwell's equations, which if you've taken an E&M class, you probably have at least seen, right? And when you get right down to it, Maxwell's equations are statements about the calculus of vector fields that we're kind of just now starting on right now. Okay. All right. Now, sadly, this next page, we don't have time for it. It is, it's a little non-standard, but it's something that y'all might see in some future engineering setting. I'm going to very quickly talk about what the big idea is. The big idea is if you have a light bulb producing a fluid, that's what light bulbs do, right? They spit out photons. And it's kind of a fluid because it's a bunch of little particles all kind of moving somewhat together. Right? If you think about it, that's what all fluids are. Right? I mean, what is water? It's a bunch of little particles called molecules that all kind of flow together in some sense. Okay. And now let's suppose you have a second light bulb that's also spitting out photons. And I'm going to color them differently just for sort of visual purposes. I'm not intending these to be colored light bulbs, right? Whatever, they're just regular light bulbs. Okay. So here's where things get weird. If I say I want to describe the resulting vector field, if I look at some point like this, and if I ask, okay, what's the flow of photons at this point? The problem is some of the photons are going that way, but some of the photons are going this way. What do you do with this, right? I can't define a vector field that says, velocity at this point. Which velocity? There's two of them. Likewise, density times velocity, looming question still stands. What is the velocity? There's two different velocities. Do I just like average them or something? It doesn't make any sense. So this is a nasty problem, and the way we get around this, and again, I wish I had time to go through the example here, but this is non-standard. You don't have to know it. It's not going to be on the test or anything, so don't sweat it. But we already have this formula. What we've done with this formula on the previous page is to say, I know the vector field. How would I compute the flow rate? And the big idea is to just turn that around backwards. Big idea is to say, look, if you want to represent this flow with a vector field, you're going to need to know these flow rates. How you find these flow rates, maybe it's empirical. Maybe you make some sort of argument on the basis of, look, there's only so many different kinds of surfaces, and I can just compute these flow rates by some sort of ad hoc argument, right? And if you know those flow rates, you can then ask, what is the vector field that makes this formula work? Does that make sense to everybody? So it turns out that this is very reasonable in some circumstances, and this example that follows is super cool. And I wish we had time, and we just don't have time. So if you want to take a look, you're welcome to. If you want to, if you have questions about this, again, you don't have to. It's not part of the material for the course. You don't have to do it. But if you're curious and if you find yourself with questions, I'd be very happy to answer in office hours. So come on in. Okay. And the last thing in this section is to talk about something called flow lines. Flow lines are ultimately a pretty natural idea. Before we get into the math, let me just conjure a visual. Imagine that there's a river, or creek, or some sort of stream of water. At any given point, the water is flowing in a certain direction with a certain speed, so we can talk about the velocity of the water. And now here's the silly question. It's the perfect time of year for this question. When leaves fall off, sometimes the leaf will fall into the stream. If at the point where the leaf falls in, if the water is moving with a certain velocity, what's the leaf going to do? The leaf is not going to swim some other direction, right? It's just a dead leaf. It's going to go wherever the water tells it to go. Right? Wherever that leaf might happen to be at any point, whatever direction and speed the water is doing, the leaf is going to do the same thing. Does that make sense? I hope that's a reasonable assertion. It turns out that's exactly what we need. That little innocent observation is all that this equation here is saying. And so let me set it up. We've got our fluid flowing. I'm going to let the vector field represent velocity. Just how you set it up to make this work. We've got also a particle that, of course, is going to move. And as it moves, it traces out a path. I'm going to say position is a function of time. So this is a parameterization of the path that the particle follows. And we can talk about the derivative of that parameterization. And, of course, derivative of position, let's think about that. Derivative of position is velocity. So this right here says the velocity of the leaf. R prime. That's the velocity of the leaf. And the big suggestion being made by this equation is the velocity of the leaf is the velocity of the water. Just like we were talking about, right? The leaf falls into the creek and the water's going that way, so is the leaf. Right? Velocity of the particle is the velocity of the fluid. And one little micro clarification, the velocity of the fluid, where the particle is. I mean, right? So we've got a leaf that fell into the water right here. It's the water right here, and what's the velocity of the water where the leaf is that's going to decide what the leaf does. What the velocity of the water is way over here, who cares? The leaf is here. So that's all this says. The velocity of the leaf is the velocity of the water wherever that leaf happens to be. Everybody buying it? So, that said, don't forget that by the setup, the velocity of the water is the definition of the vector field. And so what we have here then is our, what we call system of differential equations. It's a differential equation because it's an equation. There's an equal sign and there's a derivative, so it's a differential equation. I say it's a system of differential equations because position is vector valued. There's actually several coordinates here. In my metaphor about the leaf, there's two coordinates, x and y. And then that means this is a two-dimensional vector field. So that little system of differential equations is how you describe the path that particles in the fluid trace out, and these are called flow lines. So whatever the solution is, whatever path, whatever position as a function of time makes this equation work is the flow line. And it's just kind of a connect the dots. I mean, you just, wherever you are, you just look at the vectors, you go the direction the vectors are going, and just imagine that this is literally a river, and where would the leaf go? It's just going to follow the arrows. Okay. All right, so now here's the bad news. Bad news is we don't know how to solve these differential equations at this point. It's possible if you took 221 and if your instructor decided to do it, you might have seen how to do some of these. But I wouldn't expect it necessarily. So you probably haven't seen this, but no problem. You'll learn how to solve these kinds of differential equations when you get to Math 353. And I think most of y'all are going to take 353 next semester. Okay. We're not going to solve these differential equations. What we're going to do is talk about how to confirm solutions. So if you take, for example, this vector field right here, and by the way, you might recognize this vector field. We talked about this vector field last time or Monday, one or the other, I forget. This is what I call the stirred pot. Right? This is just kind of a counterclockwise, rotating fluid. Okay, what would you expect if you were to drop going with the stirred pot metaphor, we're making pasta. If you were to drop a rosemary leaf into that, what's it going to do? Well, let's scroll back to where we drew that. Here it is. If I were to drop a rosemary leaf, let's see, what color is that? Okay, green. Okay, there's my rosemary leaf right there. What do you think it's going to do? It's not going this way, right? It's going to do exactly what the water tells it to do. It's going to follow the flow. I think it's going to trace out a circle. Does that seem plausible? Okay. You could probably even run that experiment. Let's see, where are we? Here. Okay, so there you go. That is our speculation. This is our guess as to a solution. And by the way, typo. I'm sorry. I'm trying to remember to use this convention, R of t, to represent position, x, y, z, or x, y, whatever. And sometimes I forget and I use this other convention where I call it x of t. That was just a whoopsie. Sorry about that. This should be an R. So R of t. And so this is our speculated curve. And if you take this formula and plug it in there and plug it in there, evaluate f when x and y are cosine and sine, and then take the derivative of cosine and sine and check to see, does this equation work? And yes, it does. So confirming a solution is totally doable. You just literally plug it in, make sure the equation works. And I think there's at least one, possibly more than one, homework exercise where you're going to do that. Is that cool? Is everybody on board? right. A real quick warning. So we've been talking about vector fields, and forces are a nice example where vector fields are a useful construction. So gravitational forces, electric forces. Fluid flow are another nice application. And I like to think of forces and fluids then as two different metaphors, two different sort of, how to visualize a vector field. What should you be thinking of physically? What should you be thinking of geometrically when you're trying to, think about vector fields and different things you can do with vector fields? Some students make the mistake of thinking that you can sort of pick your favorite metaphor. Some students find the forces metaphor more easy to understand. Some students find the fluids metaphor easier to understand. Just to be clear, you need both. Both of them are going to be critical. There are certain things that we're going to do with vector fields that won't really make much sense at all if you think in terms of forces. There are other things that we're going to do with vector fields that won't make much sense at all if you think in terms of fluids. So do make sure that you think through kind of, both. Try to have some reasonable intuition for how each of these forces and fluids can be modeled nicely with vector fields. And applications coming up in chapters 6 and 7. Okay. So moving along. 3.4, this is kind of a weird section. This is, from a certain point of view, kind of premature. The tools that we're going to need to make sense out of the stuff I'm going to talk about in this section, we don't have yet. They're not getting covered until chapter 6 and 7. So, again, kind of premature. The reason that the book covers this early, arguably at least 3 chapters early, is kind of pedagogical. So chapter 6 and 7, there's a lot of ideas, there's a lot to digest, and anything that we can do early is worth it because, again, we're going to have so much to digest. Anything that we can have pre-digested will just make everything else go down a little bit easier. And it's kind of nice. So the downside is I'm going to have to tell you a bunch of stuff and then ask you to trust me on it. And I'm not going to really be able to justify a lot of what I'm about to claim here. So I'm sorry for that aspect of things. That's the unavoidable trade-off here. Okay, so that said, y'all remember gradient. The idea is to kind of separate gradient as this operator, this upside down triangle that we're going to call the del operator, from the function to which we're going to apply the del operator. Now, when you put them together like this, I hope it's not a hard pitch that that turns into that. Right? Imagine it's almost like you're distributing this scalar value to f, and it goes up to there, there, and there, and then you get exactly this. And this is just kind of what I'll call notationally suggestive, but very convenient and pretty standard. And this is a lot of things will get written this way. So, okay, well, that means del by itself is a thing. And it's a little weird. I'm writing this as if it's a vector. Vectors should have coordinates that are numbers. These aren't. This has coordinates, if you will, that are differential operators. So that's strange, right? This is weird. It's a weird kind of vector at a minimum. So I'm going to use the term symbolic vector. But we've done symbolic stuff in the past, and this notation is super convenient, and it's going to do a lot of good stuff for us. Okay. All right. So here's the first example. I'm going to define something called divergence. Here's the definition. Divergence comes from the del operator applied to a vector field by way of a dot. So now we've got to talk about what we mean by this. A dot product is something you do to two vectors. F is a vector. It's literally a vector field. It's literally made up of vectors. Del, we're pretending it's a vector. We're treating it like a vector. Right? Now again, it's a little, case could be made maybe a little sloppy. Right? But pretty standard, and it doesn't lead to any problems, and it's very convenient. So when I say a dot of these two vectors, what I mean is do the only thing that possibly could make sense. In particular, these are the coordinates, air quotes, of the del operator. These are the coordinates, literally, of the F vector field, and a dot product means you multiply. Okay, so we're going to apply the differential operators to the corresponding functions and then add. That's what dot products look like. And so the nice punchline is we actually have this expression, this symbolic nonsense, right, looks like this, and it turns out this is actually something really important. This is something that's geometrically natural. This is something that is physically natural. This is going to relate to a lot of physical scenarios. Again, it's going to come up in chapter 6 and 7, so it's a ways off. And this is worth having a name, and the name again is divergence. Okay, now, why is this physically natural? What are these applications that we're going to do with it? Yeah, we're not ready for that yet. So you kind of have to just take my word on that for the moment. What I am going to do, even though I can't justify what I'm about to show you, I am going to try to communicate about how you should visualize this thing called divergence. And here's what it is. This thing called divergence, if you're willing to trust me, it represents how much, in some sense, a fluid is flowing outward away from wherever you're evaluating that divergence. Now, I give you no justification for this. I'm just asserting, this is just a claim, right? I will give you a much more persuasive argument, a much fuller discussion. Again, later on, chapter 6 and 7. For the moment, I'm just going to assert that divergence means the fluid is flowing kind of generally outward. Positive divergence means outward. Okay, now again, not going to prove it. I am going to give you an example that's consistent with my claim, which proves nothing. But maybe it makes it go down a little easier. So here's the idea. Here's a vector field. This is what the vector field looks like. Real quick, let me point out, we're going to draw several pictures of vector fields in these discussions. I'm going to leave it to y'all to think through justifying why the pictures are what I claim that they are. I think it's a good little collection of exercises. Make sure to think them through. As always, come talk to me if you have any questions. If you have trouble figuring out why this is the picture for that vector field, I'll be happy to show you, right? Just come into office hours. Happy to talk about it. You may recognize, by the way, in this case, we've already seen something similar to this. We've seen a two-dimensional version of this where the field vector has the same formula as the position where you're evaluating it. Remember, we did one of these, right? And we ended up with a picture that looks not unlike this. What we did with the two-dimensional version, this is the three-dimensional version. So, again, you think through the details. Okay, let's compute the divergence. Specifically, I want to compute the divergence at the origin. So divergence says take various partial derivatives. Here are those various partial derivatives. I'm just plugging in. Oh gosh, I guess I have to. I'm just plugging into this formula right here for divergence. And our punchline. Okay, now why isn't this working? Okay, here we go. Our punchline is that the divergence, and let me do it like this. The divergence is positive. At this point, the divergence, we computed it, it's 3, it's positive. So keeping in mind that this is our interpretation of divergence. Divergence represents fluid flowing away from where we're looking. Good. Right? That's what the picture looks like. Positive divergence, and sure enough, look at all this fluid flow outward away from where we evaluated it. So again, that doesn't prove anything, but it tracks. It's hopefully, if nothing else, this is what the image I'm trying to conjure in your mind when we say this description up here. Okay. All right. Now I've got another example and then more stuff with more examples. Before we do, I want to address an awkward point that confused me when I was y'all's age. And I figure, why don't I try to spare y'all that confusion? And that is, what does this mean physically? Well, here's the picture. What do you see when you see this picture? And I think there's a couple of reasonable things that one could claim that you think this looks like. So let me talk through them, and let me talk through the corresponding interpretations. My first example is, let's suppose that what we have there is the top of a palm tree. So there's a palm tree up here, sort of like that, and in the palm tree there's a bunch of birds sitting around, and somebody, a car backfires, right? The birds all get scared and they fly away every which direction. Okay? So that could be what this is describing. Is that cool? A bunch of birds flying away. And with that understanding, well, let's think about how would I interpret this positive divergence in that case. I'm going to say it would mean decreasing density. Because after all, if you've got a certain number of birds, and if they're flying away, the number of birds remaining is clearly decreasing. Because they're leaving. Right? Does that seem right? So that is what I'll call the appropriate interpretation of positive divergence in this physical scenario. Positive divergence means decreasing density, and we'll make that more precise in chapter 7. But I think it's kind of believable. Here's the thing: there are other kinds of physical scenarios. So this little story about birds flying away. Okay, that's one thing that would produce a picture like this. Here's another one. Maybe I have a light bulb right there. Light bulbs emit a fluid, photons, right? A bunch of little particles all kind of moving generally together. It's kind of like any other fluid. Okay, well, a bunch of photons flying generally outward. Now, by the way, this isn't technically the right vector field and the little detail. I don't want to worry about that, right? But anyway, point being, you could imagine maybe there would be a light bulb or something like a light bulb that would make a vector field that's something like this, where the divergence would be positive, where there's this outward flow, right? So, okay. When I turn on a light bulb, is my number of photons decreasing? It's not. That's not how light bulbs work, right? So, just to be silly, light bulbs are not little reservoirs of photons where there's a huge supply of photons in there, and as the light emits light, that you get less and less photons. And when the light bulb burns out, it's not because it ran out of photons. It's not how light bulbs work. Light bulbs generate. They create the photons. So that's this other interpretation, right? So when you have positive divergence, if it's a light bulb that's creating that positive divergence, it's because you're creating fluid. You're not losing density. You're creating fluid. Totally different interpretation. because it's a totally different physical scenario. Does everyone see the sort of the contrast there? I mean, they're totally different. You wouldn't want to use the light bulb interpretation to the bird scenario. When a bunch of birds fly out of a tree, nobody's in there generating birds. Right? Is that satisfying? Okay, so just a quick heads up. So again, we are going to talk about this in greater detail in Chapter 7. And just a heads up, it's actually worse than this. It's not just that there are two totally different interpretations. It's that there is a continuum of different such interpretations. And these are just the extremes on that continuum. So we're going to talk about all of that later in Chapter 7. Okay. Another example. This is a quickie. Vector field picture. Make sure you're good with this. Again, come ask me questions if you have any. If you're not clear how we came up with that. You can compute the divergence. Yada yada yada. 0. Okay, so I claim this is a picture of what 0 divergence looks like. Now let's try to make sense out of that. How would that make sense, for example, at a point about right there in this general vicinity? 0 outward flow doesn't seem right. The fluid, after all, is clearly flowing outward from that region, isn't it? There it is. There's a bunch of outward flow. But there's also, on the other side, a bunch of inward flow. And if you interpret inward as the negative of outward, what we have is a positive and a negative, and the positive and the negative cancel. And in the net, there's a 0. Does that make sense? Again, this is just, we'll make all this precise later on. But so I guess what I should say is, does this seem believable? Is this plausible? I claim this is the right interpretation. Okay. All right. Okay, next thing we're going to talk about. Another mysterious new expression that we're going to write down seemingly out of nowhere, and that I'm going to give you no justification for yet. And we'll get to that justification again later. But this one is, instead of based on doing a dot product, this is based on doing a cross product. And remember, cross products you do by a symbolic determinant, where you take the first vector and put that in the first available row after the standard basis vectors, and then the second vector you put in the second row. So this is straight up just a cross product symbolically, but again, it's a bunch of symbolic nonsense. And wait a minute, can you do that? And wait a second, we're talking about a matrix where not only do I have to accept that there are vectors where scalars should be, I also have to accept now that there are differential operators where scalars should be. That's weird, it's uncomfortable, but it's very convenient little symbolic shorthand. And again, it gives right answers, and you're never going to get into any trouble with this formula. So this is, by the way, how I remember the formula for curl. You can multiply that out. Let me show you how to multiply this out. Y'all know how to take determinants. You go across the top, right? And okay, so let's start with here, that. I'm going to multiply by the determinant of this little submatrix, which is the y partial of F3 minus the z partial of F2. So you see what I mean? This is just evaluate in the only way that would make sense. And this little 2x2 symbolic determinant here tells you what you're going to multiply by E1. That is, it tells you the first coordinate of the curl. Is that Everybody kind of following how that computation breaks down? And you could write that all down, and you get a great big formula. And if you want to memorize that formula, you can. I never have in my entire life. I wouldn't trust myself. I am quite sure that I would get a minus sign backwards, or I'd get some of the subscripts switched. It'd be so confusing. I do not trust myself to do that. But this is easy to remember, and I already drilled it into my head a long time ago how to do determinants, and so I don't need to memorize that formula. I can just work off of this. Okay, again, we don't have the tools. Can't make sense out of this yet. Again, I'm going to make a claim, completely unsubstantiated. Hope you trust me. The point to all of this is to get some pictures on the page and get you digesting those pictures. The claim. Curl represents how a fluid is circulating. And here's the awkward part of this. I am not quite prepared to tell you what that means. So I'm going to have to do a little hand waving. Roughly speaking, this says, to what extent is there a rotation happening in the fluid? We'll make all this more precise later on. So curl is a way of measuring a rotation of the fluid. So let's see an example. I think this will make more sense with the example. Vector field, picture, think it through. Notice, by the way, negative y comma x, there's that stirred pot again. All right, and that's kind of where this picture comes from. You notice that just says that the z-coordinate is 0, so all these vectors are horizontal. And notice there's no z's anywhere in the expression, and so it looks the same at every height. So this is literally, this is a three-dimensional stirred pot. Right? Is that cool? Okay, so we compute the curl. Yada, yada, yada. Here's what the curl ends up being. The curl is this vector 0, 0, 2, which points up. And I claim this does what we claimed it does. This vector is pointing in the direction that the axis rotates around. If you think about it, our fluid is rotating around the z-axis. And the curl is pointing in that direction. It's pointing in the direction that the z-axis points. So curl is literally telling you what axis is the rotation happening around. Does everybody see what I'm talking about at this point? Again, I'm not proving anything. This is just an example. This is just to kind of conjure the image of what I'm trying to describe here in words. Again, without all the proper tools. Okay. What is harder to talk about is what's the significance of the fact that the magnitude is 2. That's a... if you want to make physical sense out of that, we've got to start worrying about units and physical properties of the fluid and stuff like this. And we can't do that until we have all the proper terms. And like I have to tell you, we need a formula for what circulation is. Right? And even then, we're going to keep it in the math zone. We're not going to get into units and stuff like that. So suffice it to say, a longer curl vector just suggests more rotation. Okay. Here's another example. This is a pretty straight up, what I'll call an easy one. So again, vector field, again, picture, again, make sure you can justify it to yourself. Make sure you can produce, this kind of a picture on your own. We can compute the curl. Curl is 0, easy calculation. Make sure you can do that, of course. No curl suggests nothing's rotating. And now let's just see, does that make sense? Does this look like there's no rotation? And I think that's pretty believable, right? I mean, it just looks like all straight lines. So I think that's pretty satisfying. Is everybody okay with that? Pretty believable. Okay. All right. The next one is subtle. The next one is a really important example. In fact, I would say the next one's a counterexample. The next one, I'm going to say, is a warning against how not to interpret this example. So let's return back to this example. We talked about the curl. We computed the curl. It was this vector. And again, I think you can kind of see there's a rotation around that vector. Right hand rule, right? Thumb in the direction, fingers going the direction that it's going. There's two different ways that you could interpret when I say rotation. I'm going to start with the wrong one. So this is the warning. This is easy to mess up. We are not talking about flow lines. Now, it looks like we are. My gosh, look at those flow lines. You can see them. They're circles. You can literally imagine some little particle of water rotating around that axis. Oh my gosh, it seems like that makes sense. And it turns out that's just not what circulation means, and it's not what gives the proper interpretation of curl in this case. It looks like it should, but it isn't. So I cannot emphasize the following enough. Do not think of curl in terms of flow lines. Here's the proper interpretation. Imagine that you have like a balloon, some object of small but non-zero size. Imagine that is floating in your fluid. And ask yourself, given the motion of the fluid as it is, how would that object rotate in the fluid? Now, we're going to get the same answer in this case. I feel like it's pretty clear that object is going to rotate counterclockwise, again, exactly as the curl kind of suggests it should. Doesn't seem like an important distinction here, but I claim this is the right point of view. The flow line point of view is wrong. Okay, and here's where you're going to see the distinction. This example right here. Vector field, picture, looks like this. Make sure you can persuade yourself, but yada, yada, yada. This is what the picture looks like. We can compute the curl, yada, 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 blah, blah, blah. Y'all can do that computation. We have a non-zero curl. That suggests, keeping in mind, curl suggests some sort of a rotation of the fluid. Where's the rotation? That doesn't look like it's rotating. These flow lines of our fluid are all straight lines. Every single one of them is a straight line. Where's the rotation? Does everybody see what I'm talking about? If you make this mistake of interpreting curl as a rotation in terms of flow lines, it doesn't work. It does not make sense. And by the way, this is not the worst such example. I can generate examples where the flow lines are literally going the opposite direction of the actual circulation. So flow lines, not the story. Case in point. Curl says there's a rotation. Flow lines don't cut it. But now let's think about the floating object. Maybe a balloon, something like that. Let's think about what the fluid will do to this balloon. And notice it's going to push the balloon that way on that side. It's going to push the balloon that way on that side. That balloon is going to rotate. Does everybody see the difference? It's not about the flow lines. Forget the flow lines. It's about how a floating object inside of the fluid would turn around. Yeah.
Is there a significance to like the -1 and like the 2?
Yes, absolutely. Great. Yeah, totally. So it's the right-hand rule thing. So looking at this example, so by right-hand rule, I mean point your thumb in the direction of the curl, then the fingers of your right hand will point in the direction of the rotation. So here, up, fingers suggest counterclockwise, which is what we actually see here, right?
Like the magnitude of 2.
Oh, the magnitude.
Like it has more circulation.
Yeah, that's right. And again, this is, if you want to really make physical sense out of that, we got to get into some physical nitty gritty that we're just not going to do in this class. So I'm going to call that somebody else's problem, right? But yeah, what you said is exactly the point. The longer the curl vector is, the more, in some sense, the more of a rotation there is. And so a Category 5 hurricane is going to have a longer curl vector than a Category 1 hurricane. Yeah. Okay, and then let's just to continue though, let's think about what's the significance of the minus sign here. Well, again, this is a vector. It points in a direction. This one points down. And again, right-hand rule, thumb in the direction of the curl, which is down. You look at the fingers of the right hand and they go, what you might want to call clockwise, and notice that's what this fluid would do to that orange balloon. Okay, there's a two-dimensional curl. It's, I don't want to say analogous because it's not quite. I mean, there is a determinant. It is a symbolic determinant, but you notice there's no standard basis vectors there. This is a scalar valued thing, so I'll say that two-dimensional curl is reminiscent of three-dimensional curl, but it is a different critter. Nice, easy little formula. By the way, I'll remind you that we have this old construction from 1.4 called the wedge product. It's kind of a two-dimensional, it's not a, it's vaguely reminiscent of cross products, but it's not a cross product. So anyway, this wedge, if you want to play this symbolic game, notice wedge was defined as this kind of a determinant. First vector there, colors, second vector there. Wedge gives kind of a nice way to denote this formula, this two-dimensional curl. Okay, I'm going to have to be really quick about this, time being what it is, but it's going to turn out, for very deep reasons that we couldn't begin to talk about in this class, it's really, really natural to take the gradient operator. To remind ourselves, gradients will take functions and produce vector fields. To compose that with the curl operator, which we just talked about, will take a vector field and produce another vector field. And to compose that with the divergence operator, which will take a vector field and produce a scalar valued function. So composing these operators in this order, it just turns out to have all sorts of benefits. And again, for very, very deep reasons. The one example I can show you right now is this claim right here. I claim that all lifetimes are 2. This is a metaphor that I don't know if I created this or if I'm remembering it from so long ago. I don't remember who told me, but I think it's a nice little metaphor. The idea is, for example, if you have a scalar valued function, and if you compute its gradient to get a vector field, that vector field, if you compute the curl, will give you 0. And I call this a lifetime of 2. If you're willing to work with me on the silly metaphor, dark, right, depressing metaphor that 0 is death, if you will. Anything that follows from 0 is also 0. I think the metaphor is kind of reasonable, but it's just a metaphor. Anyway, all lifetimes are 2. So this is a nice way of remembering, for example, that the curl of a gradient will always be 0, and various other sort of equivalent. Here's another one. If you have, let's see here, if you have a vector field and you compute the curl, and if you get another vector field that's not 0, there's no way that there could be a function whose gradient is that original vector field. Not possible. Let me make it a square, not a circle. Can't be, because if there were such a function, we would have a lifetime of 3. Right? So it just immediately lifetime has to be 2. That can't exist. Not possible. And then likewise, let's see here if I can get my eraser. Well, likewise, if you have a vector field whose curl is non-zero, the divergence of that curl will always be 0. Stuff like this. So you can see there's a million different little related kind of similar statements that you could take as like 8 different statements, or you can think of them as a single statement, all lifetimes are 2. Okay, we will say much more about this in chapters 6 and 7. We're going to draw the line right there, call it a week. See y'all on Monday. Have a good one.
Thank you so much.
Yeah, no problem. My pleasure.